We'll have a look at a typical air draft problem. With these, you have a vessel that needs to go under a bridge, and you'll either have to load cargo so as you can get under the bridge, or you can discharge a maximum amount of cargo or ballast to still make sure that you can get under the bridge. You'll always be given the distance under the underside of the bridge from the waterline, which here is 20.38. You'll be given a clearance that you'll need to clear the bridge, and you'll be given the distance of the mast from the keel. Okay, so you've got from the keel to the top of the mast, the foremast and the aftermast. You'll also be given the present drafts. Now, the present drafts only come into play when you have to calculate the initial displacement. That's the only purpose they serve. Draft forward and aft, usual procedure, calculate the initial displacement with those. They're not part of the problem insofar as using the masts. Okay, so keep those completely separate. The masts are always assumed to be perpendicular to the waterline throughout, and the problem typically asks us to calculate the final drafts forward and aft to pass under the bridge, and then the minimum weight of ballast to load, in this case, to pass under the bridge. Okay, so I've just done a sort of rough sketch here to show you. You have a bridge, the clearance you require 0.4, the distance from the keel to the top of this aft mast is 27.1 metres. You've got 20.38 metres from the waterline to the underside of the bridge, and what we're looking for is this draft here at the mast. So the mast plus the clearance is 27.5, total 27.5. Deduct the 20.38 that we have, and it leaves us with a draft at that mast of 7.12. So what you're actually calculating is the drafts at the masts. So we'll end up working out what these drafts are at the forward and after masts, and then mathematically we then have to move to work out the draft at the after perpendicular and the draft at the forward perpendicular. Now, it would be, I think it's self-evident to say that if we are trimmed by the stern, and you get your draft at the after mast, then the after draft has to be deeper than that. Must be deeper if we're trimmed by the stern. And the opposite, of course, is true with the foremast value. So when you get this foremast value and mathematically work out the draft at the forward perpendicular, then where our draft is, of course, that then has to be a negative amount. Must be negative as long as we are trimmed by the stern. The opposite of true if we're trimmed by the head. The other values you'll be given are the distance from the after perpendicular to the aftermast, and typically from the after perpendicular to the foremast. So you're given these two values. You know from your stability book the total length between the perpendiculars, so you can see with those three values we can quite easily work out those two values there. So let's look at how we set about sorting out the problem. So our length is 137.5, as I say, you get that from the stability booklet. Then we write down our clearance and mast height, subtract the bridge height, and it gives us a draft at the forward mast of 6.02 and the aftermast at 7.12. That was the example that we did. So what we're saying, okay, the aftermast, foremast, we know our drafts, we know the distances from the perpendiculars, therefore we're looking for these two drafts here. So mathematically we can say, okay, the final draft aft, it will be the 7.12. Now that will be plus because we're trimmed by the stern. When we look at our initial drafts now in the water, we're at 5.42 forward, 6.56 aft, so we're trimmed by the stern, therefore we must add that value, and it's 39, which is the distance from the after perpendicular to the aftermast, divided by the distance between the masts. So on my sketch here, the distance between the masts here, so it's 39 divided by that value, and of course for the foremast it'll be this value here divided by the distance between them. So 39 over 69 multiplied by 1.1, which is the difference between these two here, 1.10. Okay, you'll also notice, of course, it has to be the same as this value here. Mathematically it will be the same. 26, 27.1, that's 1.1. 6.02, 7.12, 1.1. So it's 7.12 plus this fraction, so it gives us a final draft aft. Then by extrapolation again, the final draft forward, and notice that it's 6.02 minus the value. So the reason we do plus and minus is because the vessel is trimmed by the stern. Once we have those values, we can do the standard computation. First of all, get your average mean draft, and with that get your LCF from the tables. Use the formula to work out your true mean draft, and with the true mean draft you can get your displacement. And just be careful, in this particular problem we are in fresh water, so make sure that you get, when you interpolate your displacement, that you use the freshwater values. So you can see we've gone to 3 decimal places with longitudinal stability, and therefore we can get our initial displacement, final displacement, and therefore the ballast to load, 1481 tonnes. Reasonably straightforward problem. As long as you can visualise this in your mind, fairly straightforward to work out the drafts at the masts, mathematically then work out the drafts at the perpendiculars, and from that you can use these straightforward formulas here to work out your displacements.